Okay, so we've got a few examples of graphing sinusoidal functions under our belt, but there's more to look at. We want to get, a good variety in. So now we're looking at this function, y equals 5 times sine of x plus pi minus 1. This function, compared to the sine function by itself, y equals sine of x, is going to have three different transformations we have to worry about. A change in amplitude, a change in phase shift, and a change in the midline. So let's get all of those down. Amplitude. I can see from here, my amplitude is going to be a 5. What about midline? Don't forget midline is y equals a constant, not just the constant. Because it's minus 1 here, I get y equals negative 1. What's my period? Okay, remember period is 2 pi over the absolute value of b, where b is the coefficient on this x here. But the coefficient on the x is a 1, meaning my period is just 2 pi. Finally, phase shift. Phase shift is c over b, and remember b is equal to 1, so it's really just c. But remember, this needs to be written in the form x minus c, not x plus c. So I'm actually going to think of this not as x plus pi, but as x minus negative pi. That means that c is a negative number, not a positive number like it appears to be. Okay, so my phase shift is negative pi over b, which is 1, which is just negative pi. And there's no reflection in this graph. Okay, so how does that affect our graph? First of all, when the phase shift is negative, the way that it is, that is going to indicate that we're shifting to the left, not to the right. Now, for all of the graphs I've done so far, you may notice that when I sketch my axes, so like this example up here, I do my y-axis, and then the part of the x-axis that I'm showing is mostly to the right of that. And that's because my graph is living all the way to the right of my x-axis, my y-axis. That's been the case for these examples as well. I haven't given myself any space on the left side of that x-axis because I didn't need it. Here, however, my phase shift is going to take this first point and move it over to the left. So I have to intentionally look at that and think, I need to make sure I have space on the left side of my y-axis here. So the phase shift is telling me where that leftmost endpoint is going to be. Negative pi. Okay? Now remember, the period, which is 2 pi, is telling me the distance from this left endpoint to the right endpoint of the interval that I'm trying to graph this thing over. So I would take my negative pi and add 2 pi to that. Negative pi plus 2 pi is pi. And you may notice we seem to have some symmetry here, which is good. That actually helps with the rest of this. So now to find a midpoint for this interval, I add these two together. Negative pi plus pi is 0. Divide that by 2, and I get 0. So there will be, one of the labels is 0, but we never label 0 because it's just the origin. Now I cut each of these intervals in half. It should be easy enough to see that this should be pi over 2, and this should be negative pi over 2. And now we have those 5 labels. I did this in the reverse order that I normally do it in, so let me go back up here and do my amplitude and midline. What's my midline? It's y equals negative 1, so negative 1. And then my amplitude is 5. I need to add 5 to negative 1, which takes me up to, actually I'm going to go to here, to 4. Then I need to subtract 5, which will take me down to negative 6. You're going to notice, let me move this up a little bit, negative 1. Things are not really to scale here, and I'm not too concerned with that. I just want to make sure I have the correct labels. There's my midline. Okay. What are we graphing? It's a sine function, an unreflected one. So we're starting on our midline, working our way up to a maximum value, back down to the midline, down to a minimum value, back up to the midline. So we're going to get a graph like this. Okay, that's our one cycle of that sinusoidal function. Not too bad, not too bad. Here's another one. We want to graph y equals negative cosine of 3x plus 2 pi, and then outside of that plus 2. Notice the negative here implies a reflection. So catalog your information. Amplitude, midline, period, phase shift. Okay? And then we know that a reflection is going to occur here, so I'm just going to write that now. Reflection. What's the amplitude of this graph? Well, it's the absolute value of A. And in this case, A is -1, which has an absolute value of 1. What's my midline? I have a +2 here. Y equals 2. Not 2, y equals 2. What's the period of my graph? Remember, the period is 2 pi over the absolute value of B. B happens to be 3 in this case. So my period is 2 pi over 3. What's my phase shift? The phase shift is C over B. Now, like in the previous example, I had a plus here, and I interpret that C as then being a negative number. Same thing is going to occur here. So C is actually -2 pi, not +2 pi. And my phase shift is going to be -2 pi over 3. Okay, that gives me all the information I need. Now again, my phase shift is going to be a negative number in this case, so that means I need space on the left side of my y-axis. In fact, you're going to see that the entire graph is going to be to the left now. So let's find the relevant information. Midline is 2. My amplitude is 1, so I go up 1 to 3, down 1 to 1. Probably should have spaced that out a little better, but that's okay. And that gives me the labels for my y-axis. Now labeling my x-axis, take your phase shift, -2 pi over 3, and that becomes your left end point for that interval. Take the period, add that to get the right end point. What is -2 pi over 3 plus 2 pi over 3? Well, that would be 0. Okay, so from here to the origin, that's the interval that we're graphing over. Now, if I start averaging these, 0 plus -2 pi over 3 divided by 2 is -pi over 3. -pi over 3 plus 0 is -pi over 3 divided by 2 is -pi over 6. And then to get this midpoint here, -pi over 3 plus -2 pi over 3 is -3 pi over 3, or -pi. Divide that by 2, I get -pi over 2. Okay? And then midline is there. We're looking at a cosine function, but a reflected one. Remember, cosine normally starts at a maximum, which would be up here. The reflection causes us to instead start at a minimum, which would be here. Okay, then midline, then maximum, then midline, then minimum. So our graph now looks like this. Okay. All right. I think I have a couple more graphing examples, and then we're going to do a word problem to wrap things up. So this time we're going to graph f of x equals -3 sine of pi x plus 4. This is the first time that our b has included a pi. It's usually a whole number like 2 or 3 or something like that. So this is going to have an interesting impact on our graph. But let's get our information down. Amplitude, midline, period, phase shift. And then this one we can see also has a reflection, so let's write reflection. Okay, what's the amplitude? It's the absolute value of A, which would be +3. What's the midline? Y equals 4. Okay, what's the period? Period is 2 pi over the absolute value of B, which is 2 pi over pi, and in this case the pi's cancel out. My period is 2. It's interesting. It's the first time we've gotten a period that doesn't have a pi in it. What's my phase shift? Well, the phase shift is 0 because I'm not seeing a C here. The C would be 0 in this case, causing my phase shift to be 0. Okay, so let's think about how we want to label things now. Sorry, I just smacked my camera. Our phase shift is 0, which means we don't need anything to the left of our y-axis. We only need stuff to the right. so I need space to the right. Also, if you think about this, my midline is y equals 4. That's kind of way up here. And my amplitude is smaller than this constant that I get from my midline, which means my graph's not going to dip below the x-axis. You'll see that pretty clearly in a minute. So putting my axes like this is a good way to start. Okay, let's find that midline now. So it's at 4. Okay. Amplitude, I go up 4, or sorry, up 3 from 4, that would take me up to 7, down 3, which would take me down to 1. And then that's it for my y-axis. Looking at my x-axis now. Phase shift is 0, which means the left endpoint of the interval that I want to graph on is 0. The period is what I add to this to get the right endpoint. 0 plus 2 is 2. All right? Now I want to start averaging this. 0 plus 2 is 2. Half of 2 is 1. And you should be able to see that the midpoint here would be 1/2. Here would be 3/2, using the same averaging technique. Okay? Now that we've done that, what kind of a graph are we looking at? It's a sine graph, and it's a reflected one. So that means I start at my left endpoint, go to a minimum instead of a maximum, then my midpoint, or midline, maximum, midline. We're going to get a graph that looks like this. That's it. Okay. One more example, and then I think the last thing, make sure, yeah, the last thing I have for you is a word problem, so we'll try and squeeze all of that into this video if we can. This last example, very similar to what we've already looked at, but we're going to have some fun fractions to work with in this case. So same thing as before, amplitude, midline, period, phase shift, no reflection in this one. Amplitude, I can see that my amplitude would be 1. Midline, y equals 1. Period, 2 pi over the absolute value of b, which is 2 pi over 4, but always simplify if you can. Pi over 2 is my period. What's the phase shift? Phase shift is c, which is positive pi over 4, over b, which is 4. This simplifies to pi over 16. And here's where the fun fractions come in. Okay, so let's start labeling and drawing things out. I have a midline at y equals 1 and an amplitude of 1. As before, I'm not going to need anything below my x-axis here. I'm also not going to need anything to the left of my y-axis because I have that positive phase shift. So starting with the midline, I have midline at 1. Put that here. My amplitude is 1, so I'm going to go up 1 from this to get 2. Down 1 would take me to 0, and we don't ever label 0, so I could just leave it like that. Phase shift, I start at pi over 16. And then, remember, I'm going to take my period and add that to pi over 16 to get this right endpoint. Okay? What is pi over 16 plus pi over 2? Well, remember what you're doing when you're adding fractions is getting a common denominator. Pi over 2 is the same thing as 8 pi over 16. And so pi over 16 plus 8 pi over 16 is 9 pi over 16. Okay? Now we average these. Pi over 16 plus 9 pi over 16 is 10 pi over 16. Half of that is 5 pi over 16. Same denominator, nothing's changed there. Averaging these. Pi over 16 plus 5 pi over 16 is 6 pi over 16. Half of that is 3 pi over 16. Now if you do the same thing here, you should see that you're going to get 7 pi over 16, which you might be able to predict, because if you've noticed, all the denominators have not changed, so you should expect to see a 16 here. And before we got the 7 pi over 16, these three numbers, we had 1 pi, 3 pi, 5 pi in the numerators. It seemed like we're looking at odd numbers, consecutive odd numbers, 1, 3, 5. You should be able to predict that 7, and then notice the 9 is what would follow from that. So there are patterns to look for sometimes. Okay, Let's graph our midline here. We're looking at a cosine function that has not been reflected. So starting at our left endpoint of our interval, we go from maximum to midline to minimum, midline, maximum. I want a graph that looks like this. All right, cool. The last thing we want to do is a word problem. And I'm not sure if I'll be able to squeeze this into this video. I might do it on a follow-up video, but I do want to talk about this for a minute because this helps us understand why we care about the sine and cosine functions as much as we do. All throughout Chapter 7, our motivation for defining sine and cosine had to do with angles. We started by looking at right triangles and then the unit circle after that. And that's kind of been our only context in which we've thought of trigonometric functions. But trigonometric functions, sine and cosine in particular, all 6 of them really, but sine and cosine in this section, are used for things that don't appear to have anything to do with angles at all. In fact, sine and cosine, the importance of those functions in a lot of applications is the fact that they're periodic. There's a lot of natural phenomenon in the world that has a periodic nature to it. An example could be the seasons. Spring, summer, fall, winter. They happen in periods, year-long periods. If you take I think there's an example in your book on this. If you take a weight and suspend it from the ceiling, for example, by a spring, and then if you release that weight, it's going to oscillate up and down. The position of that weight oscillating up and down happens in a periodic cycle, and we could create a graph that models that looks like one of these. So sine and cosine functions have a lot more to do with their periodic nature in applications than they do the fact that they have something to do with angles. So what I'd like to do, I think what I'm going to do is maybe set this problem up and then solve it in a follow-up video if we don't have enough time. But this is a problem straight out of the problem set in section 8.1 of your book. It says that a Ferris wheel is 25 meters in diameter and is boarded from a platform that's 1 meter above the ground. The 6 o'clock position on the Ferris wheel is level with the loading platform. The wheel completes 1 full revolution in 10 minutes. The function h of t gives a person's height in meters above the ground t minutes after the wheel begins to turn. What we want to do is find the amplitude, midline, and period of h of t. Then we want to find a formula for the height function of h of t, and then we want to find how high off the ground a person is after 5 minutes. So what I'm going to do is kind of sketch this out, and then we'll maybe do some of this problem. We might actually be able to get the whole thing in. Let's see. So again, we're looking at a Ferris wheel, and we have some information that we know. The Ferris wheel is boarded 1 meter above the ground. So if this is the ground, and this is not at all going to be to scale, this would be 1 meter. Okay. We're also given the diameter of this Ferris wheel. So let me give it a center here. The diameter is it's 25 meters. Okay, that's the diameter of our Ferris wheel. And then we have some more information. We know that it completes 1 full revolution every 10 minutes. Well, notice that's a measurement of time. And the function that we're talking about, the input is t, which represents time. So the output is going to represent the height of a rider after a given time. If our rider has started here, that's where he boards, and then after some time has passed, ends up at this position right here, then we would think of this as h of t, the height. And this is at some particular time, t. So I'm going to say after t minutes. That's where the rider would be. H of t represents the height above the ground that the rider is at that point in time. Okay, how do we model this with a sinusoidal function? That's going to be the goal. First thing it said is to find amplitude, midline, and period of h of t. Notice that the height of this rider is going to be periodic. It's going to happen in cycles. He starts at a low point here of 1 unit. Let's go like this. Let's be A. 1 unit above the ground. That's the lowest that the rider is going to be during this ride on this Ferris wheel. So there's gonna be a minimum of 1 unit or 1 meter. Okay. In fact, let me just write 1. There's going to be a maximum height. What's the maximum height of this rider? Well, notice from here to here, that's 1 unit above the ground. And then from here to the very top of the Ferris wheel, which is as high as the rider can get, is an additional 25 meters above the ground. That means the maximum will be 1 plus 25, or 26 meters above the ground. Okay? Now, the midline, remember, is the horizontal line that is exactly halfway between the minimum value and the maximum value. And we find it by averaging the minimum and the maximum values. 1 plus 26 is 27, divided by 2 would be 27 over 2, or 13.5. So I can say that my midline is y equals 13.5. Okay, that's what this height would be right here. So again, I can write that in if I want for reference. 13.5 meters is the height between the center of this Ferris wheel and the ground. We needed amplitude as well. So what would the amplitude be? Well, again, the amplitude is the distance from the midline to either my minimum value or my maximum value. Now, you can also see that distance is the same thing as a radius of this Ferris wheel, which would just be half the diameter. What's half of 25? Well, it'd be 12.5 meters. So that's my amplitude, 12.5. We were also asked to find the period. The period is the amount of time it takes to complete 1 full cycle, because again, the input is time. So we're thinking in terms of time here. And we're told the period in the problem. It says that it takes 10 minutes to complete 1 full cycle. So that's 10 minutes. Okay? Not too bad. B. We want a formula for the height function. We want to figure out what h of t is. Well, let's think of this in terms of a graph for a moment. Let's start the clock at t equals 0. Okay, so this is going to be like my t-axis. This is going to be like my h-axis for my height. And we're going to start the clock at 0. Now I can use this information to reverse engineer this thing. I can draw the graph and then come up with a function after that. And at time, when time is equal to 0, where do we expect the height of our rider to be? Remember, he boards from the bottom. So at time 0, our rider is only 1 meter above the ground. Remember, that's that minimum value. So I should have a 1 here. Then we know the midline of this graph should be 13.5. So I can put that here. And the maximum height is 26 meters. Okay? Now again, how long does it take the rider to complete 1 full revolution around this Ferris wheel? Well, it's a 10-minute period, as we determined. So from 0 to 10, that's going to represent 1 full trip around that Ferris wheel up there. And let me draw my midline in here. Thinking about how we graph these sinusoidal functions, I want to subdivide this thing into 4 equal subintervals. So we can see that the midpoint would be 5 here. I'll have a 2.5 here and a 7.5 here, so that everything's equally spaced. And again, we board from the bottom. We start 1 meter above the ground. Then I know I should go from a midline to a maximum to a midline back to a minimum, because again, after 10 minutes, we're back where we started, back on the ground again, or 1 meter above the ground. That's what my graph should look like. But again, the problem did not ask me for a graph. It asked me for a function. So let's think about what that would look like. First of all, this does not look like a sine function. And the reason for that is because we're not starting at the midline. It looks kind of like a cosine function, but more specifically a reflected one, because a cosine function would normally have a graph starting at a maximum. So I know I'm looking at a cosine function where a is a negative value. But negative what? Well, remember, we also use a for our amplitude, which up here we found was 12.5. A should be negative 12.5. What about b? How do we find b? B corresponds to our period in a specific way. Remember, we find period, which again, we found our period to be 10 minutes. Our period is technically equal to 2 pi over the absolute value of b. And I'm going to specifically choose b to be a positive number so that the absolute value is not going to matter. Can I solve this for b? Well, yeah. Do some cross multiplication. B is going to equal pi over 5. Okay, and I'm going to let you do the algebra to solve that. It's fairly straightforward, pi over 5. What is c? The only place c is used when graphing sinusoidal functions is in phase shift. But notice we're starting on the y-axis. There's no shifting right or left for this first point. That would imply that c is equal to 0. And then finally, what is d? D corresponds to our midline, which was y equals 13.5. I want to put all of this information into a cosine function, giving me h of t equals a, which is negative 12.5, cosine of bx, so b is pi over 5. And I'm actually not going to use an x because here we're saying that our variable is t, so it's actually pi over 5t, minus c, but minus 0 is unnecessary to write because that wouldn't change the pi over 5t here, so I'm just going to leave it at that, plus d, plus 13.5. That would be the function that I want to use for b. Perfect. All right. The last question was, how high off the ground is a person after 5 minutes? There's two ways I can go about this. I have a function, so I could just plug 5 in for t, and then evaluate all of this and get whatever the output is. That would be the easiest way to do it. You're evaluating h of 5. However, if you think of this, intentionally for a second, what is one full trip around this circle, or how much time does that take? This one full trip around this Ferris wheel. We're told that a full cycle is 10 minutes. 5 minutes is exactly half of that. So where do you expect the rider to be halfway through this trip? Right at the top, which we know is 26 meters above the ground. This should come out to 26 meters. Okay, which again, you can evaluate that by plugging 5 into this directly. In fact, you should do that to make sure you're correctly, calculating this stuff, but it will come out to 26 meters. Okay, that's going to wrap it up for 8.1.